Alright, hello and welcome. Before we get started, I'd just like to highlight that some of this will be voiced over due to the original quality, audio quality being a little bit on the poor side, as well as background interference noise at certain times. As you can see, we have 3 radiators in front of us, and what we're going to be doing is comparing OEM versus aftermarket. Do aftermarket outperform the OEM? What are the benefits, disadvantages? We're going to do this by basically looking at their quality, their appearance and their dimensions, followed up by setting them up in a test stand, logging the data from the test and see which performs best, while answering the question, does color / painted make a difference? The 3 radios in front of us are to suit a Yamaha Banshee, but before we get into it, we will quickly cover what a radiator is. Radiator, engine cooling. Radiators are heat exchangers used for cooling internal combustion engines, mainly in automobiles, but also in piston engine aircraft, railway locomotives, motorcycles, stationary generating plants, or any similar use of such an engine. Internal combustion engines often cooled by circulating a liquid called coolant through the engine block and cylinder head where it is heated, then through a radiator where it loses heat to the atmosphere and then returned to the engine. Engine coolant is usually water-based but may also be oil. It is common to employ a water pump to force engine coolant to circulate, and also for an axial fan to force air through the radiator. Alright, now that we've covered what a radiator is, we're going to look at the radiator dimensions, specs. I did record this footage, however lost it due to a battery going flat. First up, we're going to cover the OEM radiator. It had an overall height of 450 millimeters, while an overall thickness of 48 and a total width of 210, which was the same as the core's width. The core thickness, however, was only 32 millimeters. It did not extend the full thickness of the tanks. The upper tank height was 40 millimeters, lower tank height was 20. As you can see in the photo, this is how I calculated fin count per 25 millimeters by simply placing a vernier calipers set at 25 over the core and then taking a photo counting the number of fins between the calipers. We also measured the tube width, which is perpendicular to the jaws of the caliper at 2.3 millimeters. The number of tubes, so there's one tube behind the other in this case, consisting of 2 rows, and the profile of that tube was approximately 12 millimeters. Moving on to the aftermarket, I only measured the one radiator as they were both the same, just different color. The aftermarket radiator was 400 millimeters overall, with an overall thickness of 54. The width was the same at 210. The core thickness was slightly less than the overall thickness at 42. The upper and lower tank height was both 50 millimeters. Tube spacings was a bit closer together at 10. The fins per 25 millimeters was 13. It was calculated using the exact same method as the OEM, with the tube width being slightly less at 2.1. We still had 2 rows of tubes, however, being this was a thicker core, the tubes had a profile of approximately 18 millimeters. Now that we've covered the test subjects, we're going to look at the test standard. We're going to be referencing and using JISD 1614 from 2017 as our procedure. As you can see, it covers automobiles but should work equally as fine for these 3 radios. Alright, being these JIS standards are under copyright, unfortunately this is about as much as I can show you of these papers. However, this is the formula that we'll be using. As you can see, we've got several points of data that will be logged during the test that we'll be then using to input into this spreadsheet and give out our heat dissipation in kilowatts. Can ignore the frontal mass wind velocity on the right hand side for now. That is hopefully for a future video. Now you're probably all wondering why I'm going through this much effort to test these radiators. Well, quick bit of history. I have purchased one of these radiators in the past, going purely by their claims and specs of increased capacity and exceeding OEM radiators, not giving it any thought to what evidence have they shown to substantiate these claims. So a little bit more thought, and I started to buy up a few more radiators and build a stand to start testing and seeing if these claims are indeed true. You'll see by these photos they're all pretty generic style of radiator, or aluminium. Core of the radiator is welded in a vacuum brazing furnace. There's no epoxy. Tanks are 100% TIG welded, material aluminium, low price. In the next photo, same thing. Radiator is a heavy duty design. Cooling capacity is increased by about 30%. Then standard radiator exceeds OEM. When I measured the overall size of these radiators, I did not include the mounting tabs, so as you'll see, their overall size measurements differ slightly from mine, but the radiator core size should be very similar. This is the painted version of the radiator that we'll be testing also. As you can see, the low price of $88. Just in reference to the cooling system capacity, I believe that's in reference to the cooling volume. I haven't checked that at this stage, however that's something I plan to cover. This is just purely for comparison of the aftermarket versus OEM prices. Clearly the OEM is quite an expensive unit, and there would be obviously some waiting time. Now, by no means am I recommending aftermarket or the OEM units at this stage, but purely from a cost perspective, the aftermarket is far cheaper. And if you take into consideration some of the places that these machines may or may not be getting ridden, being staked or damaged becomes a possibility. Now, I know for me, if I staked a radiator, I'm not going to be happy either way. However, I would be more unhappy if I just punched a hole through a nearly $1,300 unit and would be looking at spending that money again to replace it. So yeah, cost wise, or a good alternative backup or spare, the aftermarket certainly is a viable option. Before going into the setup, just like to mention that I'm new to uploading this kind of content, and if you'd like to see more, drop a comment below as I can try to cover this in future videos. Now, starting from the reservoir, we go up through the pump, through into a flow sensor, that's just a vane type sensor, into our heating vessel, through a tap, up through a temperature probe into the radiator. Multiple temperature probes here. You can see one coming out of the radiator before returning to the reservoir, as well as there's two ambient temperature probes which will be used later, as you'll see in the formula. Now, the pump and the fan are controlled by switches that I can turn on and off as needed, and the heating elements are just simply plugged into power. And this is one of the reasons why I have voiced over a lot of this, due to the fact that I was running the elements off a generator, as the circuits in the house would not be up to handling the amount of current draw required to run it. Right, this is just a quick setup of the fan that allows easy changing of the radiators while being held closed during operation. This is currently in a startup where I'm heating the water, getting everything up to temperature. You can see the flow sensor is currently spinning. Temperature is rising. Ignore the value, it is not that low. The sensors were calibrated between the 65 and 95 degrees Celsius mark, so outside of that range they are a little bit off. I can cover the sensors and other equipment that I've used in future videos if people are interested, and the calibrating procedure behind it all. Now, this is the OEM radiator heating up. As you can see, the number of leads going to it. And this is partly the reason why I've voiced over a lot of this, is because I have a generator running in the background powering the 8.2 kilowatts of heating elements, heating the water. I'm trying to show the water level here, but it's quite hard to see in the camera, but it's roughly where my finger was pointing to. Alright, it took probably a little over 20 minutes to heat this water up to 91 degrees Celsius, where I would start the data recording, which would run for 10 minutes before stopping. Once I hit record on the computer, I would turn the fan on and let it run for the duration of the test. You'll soon see in the video I did run into a few faults during testing, especially on the aftermarket radiators. They didn't fully cover the fan shroud, so I had to improvise by placing a piece of cardboard in there to block off these holes and ensure the air was going through the core and not around it. This is the first of the aftermarket radiators, the plain one, being tested. You can see the cardboard down the bottom there. I did make sure that the cardboard did not extend up above the bottom of the tank, where it could then interfere with the air going through the core. You'll soon see in the next video where I open up the fan and show how I had placed the cardboard to ensure that it did not affect cooling. I did the same for obviously the painted radiator, as it was identical. Now, I did bring the camera over to the heater to try and catch the sound. You could quite clearly hear a low roar, same as like you hear in a kettle while it was heating and water was flowing through it. It is in its warm-up stage before the test commenced, and this is now where I've switched to the final aftermarket radiator, the painted one, and I believe at this stage I'm in the middle of running the test and recording the data. Just going to let this play in the background. This is the old video from when I've nearly staked a radiator, while summarising what we've just covered. I know I've probably repeated myself a few times so far, as well as probably left out some valuable information, but we will try cover this in future videos. As you would have previously heard before this clip started playing, was I re-edited in the raw footage of the final radiator being tested, just to show some of the background noise from the fan and the wind that the microphone would have been picking up which would have had an effect on the audio quality. I have also ordered a camera tripod so I can leave it in the stand and hopefully bring better quality videos in the future. With all the data recorded, just going to go over some of the parameters I had to conform to meet the JIS standard. One of them was the water inlet temperature. The temperature of the water flowing into the radiator shall be regulated to maintain the inlet air to water temperature difference at 60 degrees Celsius plus or minus 10 degrees Celsius in the state of heat dissipation. Some of the other parameters that I also had to meet was sensor locations and not allowing air to enter the system. Now, to maintain a more accurate and even spread on the data recorded, I allowed 30 seconds for the system to settle down before then using the information from there on in. And what I did was every 30 seconds I took them figures and amounts, put them into a table, and then got the average before importing them into here. As you'll see, we'll now enter them into the system and get our final results. Alright, before we enter the numbers, we'll quickly cover the formula. Starting at the very top here under the waterside heat dissipation amount, we have Q is the waterside heat amount in kilowatts. V is the water flow rate in litres a minute. Y, I'll call that for now, is the water mass per unit volume, basically the density at a given temperature. Being we were running around the 90 degrees Celsius mark, I've already entered that fixed value in. And then C is another fixed value, the specific heat of water. In this case, it was clear water that was being used, so that made that nice and easy. And then obviously we have our other two variables of the water temperature inlet and outlet. After that's been entered, that'll give us a value back at the top here, which will automatically transfer over to here. And then by simply entering the ambient air temperature at the time, it should give us a total amount. So I've now started entering the values into the selected cells, and it's starting to work out the amount based off the formula. Now, I did round up the numbers at the 2 decimal place mark to make things a bit easier, and I've done that across all 3 radiators to keep consistency. Now I've entered in the ambient air temperature and it's given us the final value, so I'll copy and paste that into a column here. Once I get it right, select the right cell helps. It's in, and then now I will remove the entered data and re-enter the data from the plain radiator before copy and pasting its final amount in the respected row. Now, while that's working out in the background, we'll just go through some of the qualities I noticed with the radiators. The welds are quite presentable. I wouldn't say they're necessarily Instagram type material, but certainly more than ample for the radiator and their application. Being on most quad bikes, you're not really going to be seeing these radiators or the welds in most cases once the plastics and trims are on them. So the fittings, where the tubes and the spigots going in, they seem to flow easily. There was no obstructions in them. The painted radiator, the paint seemed to adhered well. I didn't notice any flaking or peeling in places. Fitment, I noticed fitting them into the stand, the aftermarkets didn't fit as nicely as the OEM. Whether that was just errors in me drilling the holes through the board, or the mounting tabs are slightly different from factory, who knows. But it wasn't an overly major issue to fit, just a little bit more finessing. So there, as you can see, the results were quite surprising. Painted radiator performs worse than the OEM, and the plain outperformed the OEM by a marginal amount. For future videos, the plan is to look into the airflow sides of these radiators as well. We'll need to obviously remodel the test stand, including putting in the, as you can see, a mass airflow sensor to measure the velocity of the air, and through that, with the air rectifier, we should be able to calculate the air volume. Now, the other one you will see coming up in the video is then a air pressure sensor or differential sensor to check for the restriction of air going through the radiator. So we'll obviously have a tube to the inlet side of the radiator, and then the other tube would be to the outside or ambient air of the radiator, to see if there is a difference in airflow through the cores. Whether that would factor in some of the reason why we're seeing differences in cooling capacity between the radiators, as you would have very well noticed in the flow of the coolant through the radiators. The two aftermarkets were slightly less than the OEM, and even between the two aftermarket radiators themselves, being physically the same, did give out a different flow reading. So obviously internally there is some flaws or restrictions. So after further testing, it might be worth our while to cut open these radiators and see what's in there, and if materials are available, and I can get the right size core, maybe see if we can build a radiator that is more efficient than the OEM and aftermarket radiators. Obviously I'd have to make some phone calls and find if I can even get a core or in the size that we need. So, but let us know what you think, and I'll hopefully see you in the next video. Thanks for watching.